important because we want our programs actually to compile in some reasonable amount of time. But it's not always great for finding bugs. So what we've actually implemented is what we call path-sensitive analyses. And that's actually where you track information from the branches. And that can get arbitrarily complicated. So here, if you track the information from the branch, that you know that the value of x and y is either they're both 1 or they're both 2. And so you basically have this disjunction of facts from each one of the possible paths. And if you actually track information this way, the false positive that I showed earlier with the uninitialized value warning vaporizes. So that's the real motivator. The problem is that once you start tracking all these individual paths, you get essentially this big blow up. And when you start executing loops and so forth, the problem gets even more unwieldy. But we've got lots of ways to deal with it, lots of clever ways to merge paths and so forth to actually make this tractable in practice. However, in the space of bug finding, there's two things we're willing to give up. The first is completeness. So we're going to bound the amount of work that we're going to do. So we might not find all bugs in your, we might not explore all the paths within the code. And the other thing that goes back to the false positive idea is soundness. We might not necessarily prove that your program is absent of bugs. And this is actually not something that's hardwired into our tool, but you have the flexibility to make this choice. This is something that in the compiler world you would never, when you're actually compiling code, you would never do. But the goal here is to find bugs in fixed code, not to generate machine executables. So in Clang, we've implemented engines to do both flow and path-sensitive analysis. And I'll show a little bit more of how that's actually been useful. So being that we're Apple or whatever, really interested in Objective-C code. So there hasn't been really a lot of static analysis tools built for Objective-C. And so we thought, well, what kind of bugs can we actually find in Objective-C programs, given that we have Clang and it can parse C and Objective-C. And so it doesn't really matter if you know anything about Objective-C, except it's just the language of choice to build iPhone and Mac apps. So it's kind of important. And it's basically just another version of C with OO extensions. The thing that matters here is that we have this kind of memory management model built into Objective-C, where you have these reference counts that are embedded in objects, and that by program design, you're supposed to use these counts in a certain way to kind of guarantee an absence of leaks. So this is like something very systematic so that programmers can follow this and so their code is leak-free. So naturally, this is something that we can check with static analysis. You've also may have heard that Objective-C also supports garbage collection now. But like anything, you're retrofitting this technology into a 20-year-old language. There are many subtle rules you need to obey in order to guarantee that it works, and we can check those as well. So I'm just going to walk you through this idea of how we actually check these kinds of leaks. And the same principles apply to any other kind of API, like malloc and free, fopen, fclose, lock, unlock, whatever. There's all these, contracts, protocols, whatever, that we write and use all the time. A lot of these could be systematically checked in the same way. So ignoring the syntax, basically on the top line, we'd allocate some string. And it has a reference count that the programmer is supposed to release. We then pass string to some method foo, and we don't really care what it does with it. Foo can add or decrement reference counts to it, but essentially the reference count that we know for stir in this scope, we're responsible for decrementing ourselves. And so it's this very localized way of thinking. If you see a certain amount of counts in your scope, you're supposed to decrement them. And that's exactly what we do on this last line. Now, if we actually drop this statement, we have essentially there's going to be a leak at some point. Maybe not right here. Foo may have actually incremented the count, but then later on there could be a leak somewhere else. And that's actually kind of what makes this a little insidious to find these bugs using a dynamic tool, because the leak can occur long after the problem where it actually occurred. So here's an example of diagnostic emitted by the tool on an open source program. Now, the bugs I've seen on Apple code are more interesting, but this is actually this is a pretty common idiom. So essentially, this array is allocated every time this method is called, and then on some branch condition, they just abort. And because Objective-C doesn't have RIIA, there's just a leak here. They never decrement the actual count. And the nice thing here is there's this nice sequence of paths that say exactly what happened. You allocated this object. It's no longer used at this point. You never decrement it. You have this surplus reference count. Tells you exactly what happened. So how does that actually logically work? Essentially, there's this abstract type, this DFA that's being tracked by the static analyzer on a pointer value that's returned from a method call. And so you can, plug in your equivalent thing, like, whether something's in the lock state and should be unlocked and so forth. So essentially, when an object is returned from an allocation, we say it's owned with a +1 count. You can increment and decrement the counts as much as you want. If you decrement it to the point where there's no more counts anymore, you should consider it released. It may have actually not been released in this current, immediately, but you should no longer consider it available. And then any use of it afterwards is considered a serious error. And then a memory leak is basically any time you lose the reference to the pointer and it's in one of the blue states. So this is really simple, right? This is the same discipline that the programmer is thinking about. We've just enforced it into the tool. And there's similarly another state machine for cases where initially you don't have an owning reference to the pointer and you increment and decrement the counts. And so implementing this is actually not that hard once the base infrastructure is in place. And so we think there's a lot of traction in Clang to actually build a lot of domain-specific checks using this very simple kind of reasoning. Things I haven't talked about, there's other ways to do clever tricks in Objective-C, these memory pools, garbage collection stuff. We're obviously, thinking very hard about it. We can address a lot of these, and we're thinking about very much how do people use these rules in practice, just so to make the tool very useful. I showed earlier in some of my slides about, we're doing pointer tracking, so we're doing aliasing along individual paths, so you have very precise information of what points to what. And there's lots and lots of room for improvement. The thing I want to mention is this is basically all in the core infrastructure. So if you were interested in writing your own specific checks, you don't have to reinvent this wheel. So so far this has been very successful. We've been using this checker in particular internally at Apple.